Okay, so here's a problem. It's a little bit miserable. You never know, I might be miserable and ask you that. So what we're going to do is the integration by parts again, and we want to remember Lipit. So I don't see a polynomial, I see an exponential, and I see trig. So I'm going to let u be the e to the x. I'm going to let dv be sine x dx. The derivative of du, derivative of u is e to the x dx. The antiderivative of sine x is negative cosine x. We're going to remember the integration by parts formula, uv minus the integral of v du. So e to the x, negative e to the x cosine x, plus, because of minus, right, e to the x cosine x dx. Well, I don't have the same thing, but I'm going to keep going. So I'm going to let the same kind of u substitution happen. E to the x cosine x dx. The derivative of e to the x is e to the x dx. The antiderivative of cosine x is sine x. Alright, so we're going to set that up. I hope you don't mind me not putting the u and the v here. I just did that same box. So I've got this original, negative e to the x cosine x. I've got a new e to the x sine x minus the integral of e to the x sine x dx. And that's, you know, what that looks like is that looks like the same original integral that I had. So what I'm going to do is, and this is the trick with this one, I'm going to set that equal to that integral, e to the x sine x dx. And what I'm going to do is I'm going to add this to both sides. Which gives me 2. So I've got negative e to the x cosine x plus e to the x sine x equals 2 of the integral e to the x sine x dx, which just means I can divide both sides by 2. And that's what I did to get that answer. Okay. Let's see. Next one. We're going to solve this initial value problem. Well, the first thing I'm going to do is I'm going to rewrite this dy dx. And then I'm noticing I get an e to the y on opposite sides of the equation. So I'm going to move that x e to the y to the other side. And then I'm trying to separate the variables here, right? I'm trying to get the dy with the y's and the dx's with the the x's with the dx's. I can factor out an e to the y. And then I can divide by e to the y. And I can multiply by I'll multiply by the dx. Okay. And then let's rewrite this as e to the negative y dy equals 3 plus x dx. So here we go. What's the antiderivative of e to the u? It's e to the u. So I can just write that as e to the negative y. But if I were to take the derivative of this, I would have an extra negative kicking around. So I got to remember to stick the negative there. Remember, we have a plus c over here. But if we have that same thing on the other side, a different constant on the other side, we'll still have a constant. So the antiderivative of 3 is 3x. The antiderivative of x is 1/2 x squared plus c. I'm seeing, let's see, what am I seeing? I know I've got this point 0, 0 that this curve's on. Let's find c right now. So negative e to the 0 equals, well, that's 0, that's 0. So that's c. So it looks like c equals negative 1. At least at this point. So I've got negative e to the negative y equals 3x plus 1/2 x squared minus 1. Well, it'd be really nice. Remember, I got to solve these things for y. So if I divide everything by a negative, change those signs. I'm just writing this in a descending order because I felt like doing it. Now I can take the natural log of both sides, right? Feels like I'm coming out with an extra negative here. In fact, I know I am. Just a minute, I'm going to take a look. I don't see my mistake with this negative. It is an extra one, though. I'll look at it again and I'll talk to you about it in class. Okay, I'm not seeing where it's coming from, and I want to get this video recorded. Okay, let's do the next one. So how do you, I gave the answer to you on the paper, but here, how do you deal with this? I'm seeing a bunch of sine waves here is what I'm looking at for that slope field, and I know this point goes through 0, 1. So there's the 1. So I'm seeing something that looks like this, dips down a little bit, comes back up. It's close enough for that. Okay, if this had been through a different point, if this had been through the point -1, -1, 2, say. Whoops, what's happening here? If it had been through the point -1, 2. Well, then it would have looked something like this. -1, 2 is about more or less there, so then it would be following that path. Okay, and that's how you graph a solution into a slope field. Okay, it's that easy. Okay, next question. Another separation of variables problem. Well, with this one, if we bring the 3y squared, whoops, let me go to a black pen. A 3y squared dy equals cosine x dx. Well, now we're set to take the antiderivative very easily. Add 1, which is 3, divide by 3 leaves me y cubed, plus some number c, but in the antiderivative of cosine x is sine x, plus some number c. Then they're telling me that I've got this point pi 5, so I'm going to get 5 cubed equals the sine of pi plus c. Well, the sine of pi is 0, so that leaves c, and 5 cubed is 125. So I can come back up here, replace that 125 with a negative 125. I'm sorry, it's a positive 125. What am I doing? And then I'm going to take the cube root of both sides to solve for y. And that's how I came up with that answer. Alrighty, for this one is a differential equation. There is one of these on the test. So if they want us to write a differential equation, we got to write dp, because that's the variable. dt equals, now they're telling us the constant right here, so I can write that in. If they didn't tell us the constant, I'd have to write a k. Now, I'm hoping what you remember from doing all that work is that you can jump to this expression where there's an initial value, but we know the initial value. So 56,800 e to the 0.031t. And that is A and B for this question, and that's all there is to this part. Okay, you have to evaluate it. I'm going to substitute one for t, and you'll see. So this one, they're telling me this is a decay equation. I know that what's the half-life of this element was that what we're looking for. Well, this we can solve. I know if I divide whatever amounts there is, if I'm looking for the half-life, when I divide what there is now, divide what there was originally, that better be equal to 1/2. So that leaves me with this equation, very easy equation to solve. You take the ln of 1/2, and the ln of e to that power just leaves the 1.2t. So I'm going to divide this by the negative 1.2, and that will be the half-life. And I'm not seeing my answers here. Oh, it's just a minute here. You have that. I got a half-life of t equals 0.578 years. 8. Okay, then they're asking us, when will 98% of it decayed? Well, if 98% of it's decayed, 2% will be left. So, when is that equation? When is that? We know that 100% of what we started with, we want to know when that's equal to 2%. So if I divide by 100, that leaves me 0.02 equals e to the negative 1.2 t. Again, take the ln of both sides, divided by negative 1.2. That'll be our time, and I got, what did I get? 3.260 years to 3 decimal places. Okay. Next question. Last question. I've got 4 minutes to keep this video under the right time. So what we need to do is, how far will a car coast before reaching a complete stop? That's asking me, when is this velocity equation equal to 0? So a couple of things. We know that the initial speed is 20. So that's what v sub 0 is. And then they want to get this exponent. I know it's the initial, it's this k number divided by the mass. So that's negative 80 over 1200 t. And I want to know, when is that equal to 0? So there's nothing that's telling us we can't use a calculator for this kind of equation. So what I did is I typed in that equation in y1. Notice I put in 8 over 120 instead of 80 over 1200. I didn't do any further reduction than that. I did cross off the zeros, and that's just to save me a minute to type keying it in. And then for my window, I had no idea what to use. So I said x min was 0 times 0, and I guessed 100. And then y, I had a nice small y window because all I really want to see is when it's getting close to 0, right? So I graphed that. And boy, it's looking, let's see. That's at 50. It's still got a little bit of speed. What's happening at 75? Well, there's still a little bit. How about at 90? Still even a little bit. So I said, how about 100? See, I'd say that 100, it's pretty close to 0. I did some calculations. You can verify it. But it's just about stopped, I thought. So how far will it coast? Well, I know it's pretty well stopped at after 100 seconds. So then, since I know I want to find out how far it's traveled, this particle's traveled, I'm going to take a definite integral from 0 to, I said 100, of that function, right? Of that 20e to the negative 80 over 1200 t dt, and I don't really want to integrate that by hand. So what I'm going to do is I'm going to grab my calculator again, and I'm going to use fnint. I do actually do it on the screen. I won't do that because we haven't done that. But remember, I have that equation in y1. I can do, what I can do is, what is it, 9? I can just type in those key presses, and that'll dump that y1 function there. X comma 0 comma 100. And they want this rounded to the nearest whole meter, so it traveled about 300 meters. Okay, so about 300 meters in that 100 seconds. So then they're asking me, how long will it take this car's speed to drop to 500? Well, this is just pre-calculus kind of idea, algebra 2 kind of idea. all we're going to do is we're going to go back to the functions. I'm going to have it graph the equation y equals 5. I remember I got to change my window because I was up to only going up to 3.1. I'm going to graph it. There's an intersection, and we're just going to let the calculator find it for us. So at about 20 point, what do they want? Nearest tenth of a second, so at 20.8 seconds. And that's where I came up with my answer. And that's that practice test.